Hi there, welcome to video number 11 in the calculus of variations. In the last video we looked at the problem of a ball rolling down a track and tried to find the equation that described the minimum time of that. The equation that gave the curve that would define the curve of minimum time. Now the equation that we came up with was an equation of this form. It's x equals a theta minus sine theta, and y equals a 1 minus cos theta. Now, and I said that there was the equation of a cycloid. Now, what does a cycloid look like? Well, if we were to take the circle and we were to take a point on that circle, there's a point here, and if the circle was to, just a wheel, if the circle was to roll in that direction there, and we looked at the curve that this point here would map out as the circle moved along that line, then this curve would map out, would look something along these lines. Okay, and then it would repeat again. Of course that's meant to be symmetric. Okay, and it would keep repeating. Now that there is a cycloid, and that gives us the curve which would minimize the time of descent of a ball here. So this part of the curve here would be part of a cycloid here that we would see. Now the cycloid is given by this equation, so how did we get to that equation? Now there's a nice little derivation that I've seen online which I'll just repeat here, and I'll put a note down where I got it. Now if we were to do a coordinate axis, okay, we can call that y and call it x, if you like. Now if we took a wheel, just a circle. Oh, circle's not a very good circle, is it? I'll try and get something better than that. Not very great with this tool, try to get circles drawn. So I'll draw a circle, and I think then after I've drawn the circle, there we go, there's a circle there. Okay, still not fantastic, but there's a circle. If we take that point there to be in the centre of the circle, and we call that point C, and if we come down here, the circle's meant to be sitting actually on the axis. Okay, right, we call that point D. Okay, now we know that this length here, the length D that it's travelled, it will be equivalent to some arc length here. Okay, so we can call that arc length there, just call it K. Right, now let this point here be a point on the circle which we're looking for, which is P, comma X, comma Y. Now that there is the parametric, we're looking for a parametric equation in X and Y, and that's a parametric equation there. We're going to show that that parametric equation there, if I call that, that would be P subscript X, and that would be P subscript Y. Now if we look at a point C, point C would be that distance there, which is d, and that height there, which is the radius. Okay, and the radius is, in this instance, we could call the radius 1, but we also know that value d is the same as the arc length k, so we could say that c equals, you could call it k, comma 1. Okay. Now, what we're looking for now is if we take this point here, this value x and y, if I was to draw a curve, draw a line joining the two, okay, now we're looking for, to get this point here, to get the y coordinate, we would be adding this height here to that height there, and the x coordinate would be this distance here plus this distance here. Okay, so now if we do the x coordinate first, then we know that if we call that angle there alpha, getting quite small now, that's alpha, you can see that, that's angle alpha, then this distance here will be simply be sine of alpha, is this distance here, so we could say sine of alpha equals this distance here over 1. Now if we call that distance there, we'll pop that down to that, that point there, we'll call that point B. Then we could say sine alpha equals the distance BD, which is this distance here, which is the same as that distance here, BD upon R. In this instance it would be equal to BD upon 1, which would just simply be BD. Now this angle here is the actual angle that we're interested in. This angle here is, we call that angle theta. Now that's the angle we're interested in, because that's the angle that the point here on the curve makes with the center point here, C. Okay, so you can see that that arc there is given by the angle theta there. As angle theta increases, the angle, the length of the arc increases. As length of arc increases, the distance along here would increase relative to it. Now we can find that, and we can find these values in terms of theta if we note that sine of 180 minus alpha, right, that's theta there is 180, that's 180 minus our alpha. Well, sine of 180 minus an angle is just the same as the sine of the angle. Okay, that's the same as the sine of the angle, so that's the same as sine of angle theta. Okay, so it means that what we can do is we can write OB, right, there's OB there, that's O there, that's B, so OB, that distance there, which is the x distance we're looking for, is equal to OD, that distance there, OD minus this distance here, BD. That is equal to, well, OD there is the arc length K. The arc length K is simply given by theta, and BD is given by a value here which we just worked out, sine theta. So all we're taking is the x coordinate is this distance here, this distance is that distance, which is the arc length theta, minus this distance here, which is this little distance up here, which is the sine of that angle there of theta. So we can write up here P of x equals theta minus sine of theta. So that's one of them that we're interested in, and you can see that is in the correct form, theta minus sine theta. Okay, and now if we want to find the y coordinate here, the y coordinate we could say, if we let that point there be r, okay, then the distance in the y coordinate is dr, so d to r will give us the y coordinate of this point P. So we would have dr equals dc plus cr, dc plus cr. Now we know that dc is just the radius of the circle, which in this instance here we'll call 1, plus cr, but cr is the cosine of this angle alpha. Okay, so that's 1 plus cosine of alpha. Now from the trig identities, the cosine of 180 minus alpha is equal to minus the cosine of the value. So we can then write that there as dr equals 1 minus cos of theta. Okay, so now we've got our y value, py equals 1 minus cosine theta. So now we've got px and py, so we can look at px equals theta minus sine of theta, and py equals theta minus, get the number out, yeah that's right actually, yep, and py is 1 minus cos theta. Now that's in the similar to what we have up here. The only factor is we've got a factor of a. Now we've done that derivation assuming that the radius is 1. Now if we were to choose any other value for the radius, it would be equivalent to multiplying each of these by a constant, and we'll call the constant a, which in effect becomes the radius. So we would have px would equal a, which is the radius, theta minus sine of theta, and py would equal a1 minus cos of theta, which is a parametric equation which we were trying to derive. So that there is a px and that's a py, the same as a px and a py here, and you can see where each of these things come from. The a is the radius and theta is this angle here that's mapped out as this ball or circle moves across in that direction. Now that there is a parametric equation of a cycloid, and that's the description of the solution of the brachistochrome problem. Okay, thank you for listening to this video, and I'll get you in the next video. Goodbye.